Hi, I am Professor J.K. Ray of IIT Kharagpur. For last 4 lectures, I delivered on nitrogen containing organic compounds, and today I am delivering the last of this 5 lecture series, where some more interesting features of nitrogen containing organic compounds will be discussed. Yesterday, or that 4th lecture, I said about a very interesting type of nucleophilic substitution reaction, that is again being shown here. When RBr means alkyl bromide is treated with silver cyanide, we get RNC, and when RBr is treated with sodium cyanide, we get RCN. That means, in the first case it is the nitrogen acting as a nucleophile. In the second example, it is the carbon of nitrile is acting as a nucleophile. Why this difference? That is being written over here, and also I explain that capability of silver plus to precipitate silver halide is much better than sodium plus to precipitate sodium halide. So, that helps the more electronegative nitrogen to attack in the first case, and which follows a mechanism SN1. And in the second case, it is a straightforward, no precipitation of like the previous one. So, it is a 2-stage process. It is a substitution nucleophilic bimolecular, rather one transition state process. I will tell little bit about the SN1 and SN2 reactions now. So, in the second case, the transition state for SN2 reaction, look very carefully that SN2 is written S capital in subscript and 2 in the same size as that of S, not SN square. Some people write SN square, no, that is wrong. So, it is the abbreviation of substitution nucleophilic bimolecular SN2. What it does? A nucleophile with the pair of electron or the negative charge attacks the substrate, and the leaving group, that is X, leave, and the nucleophile enters from the opposite side. So, leaving group and the nucleophile making an angle of 180 degree. So, this type of thing is called backside attack. So, what happens? The inversion of configuration is taking place. You can see X is on the right hand side in the substrate and Y is on the left hand side of the substrate. So, this sort of thing is called, if the compound is chiral, the plus will be converted to minus and the minus will be converted to plus. So, this is the SN2 type reaction, and this inversion is called Walden inversion or Walden inversion. So, inversion of configuration is a very important phenomena. What are nucleophiles? Nucleophiles are electron rich species which reacts with electron poor species. Of course, electron rich will not prefer electron rich, there will be repulsion. So, it will prefer the electron deficient species. What are the nucleophilic substitution? One nucleophile replaces another. The nucleophile which is being replaced is called the leaving group, and the nucleophile which is entering is called the entering nucleophile. It occurs when an electron rich species, that is the nucleophile, reacts with an electrophilic saturated carbon atom, is attached 2 times is written to an electronegative group, that is very important, which we call the leaving group. So, leaving group is one sense is also, when it is leaving, is a nucleophilic type, and nucleophile will be much more stronger than the leaving group 1 so far as the electron density or negativity is concerned. Nucleophile adds first and leaving group go later. Does it happen? So, nucleophile being added. So, we can see a pentavalent carbon species like this, and then the leaving group leaves and nucleophile enters. Another possibility is leaving group goes first and nucleophile comes later. That means, out of these 4 substituents on the carbon, that is the substrate, X is leaving first, making the carbon as carbocation, and then the nucleophile attacks. So, this is one type of reaction. Nucleophile attack and leaving group goes simultaneously. That is a very important feature. Y minus is attacking, X minus is leaving. This is a concerted or simultaneous process. So, these are the three possibilities over there. What we see? We do not see any example where nucleophile add first and leaving group go later. We see some example where leaving group goes first and nucleophile comes later through the formation of carbocation, and this mechanism is called substitution nucleophilic unimolecular, abbreviated as SN1 type. Now, nucleophile attacks and leaving group goes simultaneously, that is a concerted process, should be classified as SN2. So, I have in brief said about SN1 and SN2 type reaction in connection with the carbon nitrogen nucleophile, where carbon is attacking in one case, nitrogen is attacking in the other case in nitrile. Two types of discrete mechanisms are there. One is SN1, already explained, substitution nucleophilic unimolecular, not first order, R x slow, R plus, x minus, then y minus first, R y. So, rate will depend only on the slowest step, that is the concentration of R x. It is the molecularity is 1, not the order. And SN2 type is S stands for substitution, N for nucleophilic, 2 for bimolecular, where it is a concerted process. The concentration of both the nucleophile and the substrate is very important in predicting the reaction rate. So, rate depends on the concentration of both R x and the y minus. So, SN2 hydrolysis of bromomethane in aqueous base proceed according to the rate K CH2Br OH minus. Let us take an example. Is it so? How it happens? That CH3Br when treated with OH minus, it forms a transition state like this, and then it gives a product. What is happening? The bromine has left, OH has entered. Both alkyl bromide and OH are participating in the rate limiting, that is slowest step of the reaction. That is why both the substrate and the nucleophiles concentration has been considered in the rate determining step. We know if there be a multi-step reaction, the slowest step is the rate determining step. As it is only one step reaction, only one transition state, so it will go from substrate to the product through the formation of an activated complex, that is called the transition state. OH minus becomes partially attached to carbon before bromine minus is fully detached. So, one detached, another attached, and that happens simultaneously. Energy necessary for breaking carbon bromine bond, where from it is coming? It is supplied by that produced in forming the HOC bond. So, one bond is broken, another bond is made. So, energy being compensated or energy being utilized in that way. Quantum mechanical calculation shows that an approach by OH minus along the line of centers of the carbon bromine bond is of the lowest energy. That is a very important feature for SN2 type reaction. Nucleophile attacks bimolecular process, rate depends on both the molecularity of the substrate and the nucleophile, and the sp3 hybridized carbon changes in that way. Nucleophile attacks from behind the carbon chlorine bond. This is where the sigma star antibonding orbital of the carbon chlorine bond is situated. This is a very important feature. Carbon chlorine bond having two lobes, one the filled one, that is carbon chlorine with the 2 electrons staying over there, but there is a tiny lobe on the opposite side, that is called antibonding lobe, very clearly shown over here. So, this is the antibonding lobe, this is the bonding lobe. So, bond formation takes place from the antibonding side and bond breaking takes place from the bonding side, and it is some sort of oriented in this fashion. So, this is called transition state energy maximum, where the carbon is apparently shown as sp2 hybridized. Rate depends on both the molecularity of both concentration of R halogen in this case and nucleophile, and ultimately nucleophile enters from the opposite side of the leaving group and inversion of configuration takes place. Inversion of configuration is a very characteristic of SN2 type reaction, and racemization is a very characteristic of SN1 type reaction. This is the difference. What are the reactive intermediates? If I take this energy profile diagram, where energy being plot with the reaction coordinate means many features like time, temperature, bond distance being plot. So, A plus B gives rise to a transition state, then it comes to a little bit energy minima called intermediate, then another transition state and give the product D plus C. If this be the energy profile diagram, then this C point will be called the reactive intermediate. That means, it is an intermediate, but it is also reactive, which will combine with the nucleophile to get the second transition state and then the product. Rate will depend on Ka. Energy minima is the reactive intermediates thing, and we know A plus B when going to this transition state, that will be delta G plus the first one, and delta G prime in the second case is little bit less compared to the first one, and the energy difference between the starting material and the product is delta G 0. See, SN1 and U1 reaction mechanism are more or less similar, and the radical chain reactions also are of same type. Now, this will be very clear to explain the fact of the bonding orbital. Say methyl chloride, as I showed, as I gave you the first example. So, bonding orbital is this one, and this is the anti-bonding orbital of X. So, each one have a bonding side and an anti-bonding side. Anti-bonding side is smaller in size orbital coefficient, because there is no electron, but bonding one bigger in size, and this is in one phase, this is in the opposite phase, that is why it is made little bit darker and this is white. So, when the nucleophile comes, the bigger one will overlap with the bigger one, or the black will overlap with this black orbital, and then what will happen, the tiny one on the other side also overlap with the tiny one of the X. Then what happens, filled orbital of nucleophile and empty orbital of carbon halogen bond, that is the sigma star orbital. There are two orbitals, one is sigma and another sigma star, that then it produces a transition state like this, where nucleophile is going and leaving group is still attached. You get a apparently pentavalent type of transition state. So, new sigma bond being formed, old sigma bond being broken, and p orbitals of the carbon atom being shown in that way, and ultimately the substrate has changed to the product when the reaction is over. Nucleophile has entered from the opposite side of the leaving group. So, this is a very good orbital picture of the SN2 type reaction. This is also very clear when OH minus attack the carbon bromine bond, bromine is little bigger, it is being shown with colored things. Carbon bromine sp3 hybridized methyl bromide, OH minus is attacking, again from the tiny side the overlap is taking place, OH being attached, bromine still attached. So, this is the transition state. Then you get the product where the inversion of configuration has taken place, bromide has left. In normal structure, it is written over here, OH minus attacking the methyl bromide from the opposite side of the bromine, inversion of configuration is taking place, bromide minus is left out, that is as a leaving group, and methyl bromide is now converted to methanol. Important point in this case to remember that inversion of configuration does not mean R going to S or vice versa. Some people have a concept that always R will be changed to S or S will be changed to R. That happens in maximum cases, but R and S is the abbreviation of rectus and sinister, that is absolute stereochemistry's notation, but that is the thing scientists saying that these are the priority rule you have to apply. So, based on R will not be changed to S, S will not be changed to R, but one thing is for sure, inversion of configuration means if the from the polarimeter the data of the substrate is plus optically active compound substrate, the product will be the minus or vice versa. So, that means inversion of configuration means it is an SN2 type reaction, and if it is an SN1 type reaction, there will be racemization. Okay. It is like inversion of an umbrella in a storm. This is the thing happened, this is the cartoon picture, umbrella was this way, it has been converted, inverted in the other side. So, it is called a Walden inversion. This is a good example. Let us take a chiral carbon, all 4 substituents are there. This is in plane bond, this is also in plane bond, that is the iodide, iodide is the leaving group, C6H13 is one substituent, methyl second substituent, hydrogen third substituent. The specific rotation of this compound is found to be plus something. Now, these 3 groups are being shown in different types of bond. As I said, the normal line means in plane bond, broken line means below the plane bond, that is called alpha bond, and thick line means above the plane bond, that is beta bond. So, this is the absolute stereochemistry of the starting material. When we are treating with iodide, because already I is here, just to differentiate this, isotopic iodide is being taken. What will happen? That will act as a nucleophile, that will attack to this carbon from the opposite side of I prime will enter or I star will enter and I prime will leave, and what will happen as a result? The inversion of configuration is taking place. What is the proof? If I put it in the polarimeter, we will see the I plus has been changed to the specific rotation has changed from plus to minus. That is the thing I said. R normally changes to S normally changes to R, but there are some examples where R remaining R, S remaining S, but plus will always change to minus or minus will always change to plus if it is an SN2 type reaction. So, inversion of configuration means notation, that is plus to minus or minus to plus, not necessarily R to S or S to R. Rate of racemization twice the rate of inversion or incorporation. So, reaction profile of SN2 will be very straightforward: initial state, transition state, final state. So, this is the free energy diagram, and very clearly it is energy profile diagram, very clearly shown the transition state, only one transition state and a concerted process. For SN1, the hydrolysis of tertiary butyl chloride by base proceed according to the rate where K1 is T-BuCl concentration or independent of OH minus. That means, in this case the nucleophile is OH minus, but its concentration has nothing to do with the rate determining step. Why? Because in tertiary butyl chloride, it is the sp3 hybridized carbon and with the attached with the chlorine. Chlorine is leaving and that will leave first. Why? Because 3 methyl group is quite bulky and moreover it pushes electron to this carbon, helping this carbon to release the chlorine very easily, and as a result it gets converted to the carbocation, means positive charge, planar. Though it is shown in this way, it is planar. So, what is happening? sp3 hybridized thing has changing to sp2 hybridized thing. So, this is the slowest step and this should be a rate determining step. And next what happens? OH minus is the nucleophile that will come, that might come or attack this carbocation from right hand side and from left hand side with equal ease, because it is the flat molecule. The attack from top or attack from bottom is of equal rate. As a result, there will be the plus and minus will be of equal amount, and if I mix plus and minus together, the resultant thing will be plus minus. We call it a racemic, that means it is 0 rotation in the polarimeter. 0 rotation in the polarimeter happens in number of other cases if it is not a chiral compound, then or if it is a meso compound, and third case is of course it is a racemic compound. So, in SN1 the racemic mixture will be formed. Halides undergo slow ionization to yield the ion pair R plus and Cl minus, followed by first attack by OH minus or solvent or nucleophile to give the substrate. The energy necessary to effect, always this energy balance is important. The energy necessary to effect the initial ionization is largely recovered from the energy evolved through solvation of the resultant ion pair. So, this is happening in SN1 type reaction. What are the factors which affect the rates of SN1 and SN2 reaction? The structure of the substrate. We found that a methyl halide undergoing SN2, tertiary butyl halide undergoing SN1, then what happens the in between substrate. Concentration and reactivity of nucleophiles are also very important, especially for SN2 type thing. For bimolecular reaction only, the effect of solvent is also a determining factor, some protic solvent, some aprotic solvent, that also changes their reaction rate tremendously. The nature of leaving group called nucleofuse, because what type of leaving group is there, is it easy to leave or it is difficult to remove, that is also very important factor, because the bond strength is the important factor over there. And stereochemical implication of the mechanism, as I told you already, the inversion of configuration SN2, racemization is SN1. Say as I told you the first case methyl bromide, without looking at that as carbon being attached to 3 tiny hydrogen, this should be attacked from the opposite side of the carbon bromine bond very easily. So, it will undergo very facile SN2, and the last example where the tertiary butyl bromide is there, that is just the opposite effect. The attack of the nucleophile from the opposite side of the bromine is very much difficult because of the steric factor and electronic factor. So, what it will do? It will first release the bromine as bromine minus, and it will be converted to carbocation, and then it will react with the alcohol and or OH minus, whatever the nucleophile is, to give the product. What will happen to ethyl bromide and so isopropyl bromide in this type of cases? Ready hydrolysis takes place, methyl bromide and tertiary butyl bromide. I have explained why. More resistance in case of ethyl bromide and isopropyl bromide. Why? Look at the data, Rx y minus, Ry x minus, and if we follow the reaction mechanism very cleanly, we will find that SN2 rate will be maximum for methyl halide. Look at the data, 6 into 10 to the power 3, and SN1 rate is found to be 0.002, almost negligible. And the last case where the SN2 reaction is very slow, that is 0.00005, again you can neglect it, and the SN1 rate is 4 into 10 to the power 6. I explained why. And in between thing, you see more SN2 in the ethyl case, less SN1 in the ethyl case, and in the isopropyl case it is a 50-50. Both SN1 and SN2 mechanism is being operated. So, in a nucleophilic substitution reaction, both when carbon and nitrogen are the nucleophile, and using the metal ion we did that bidentate, or I should say that ambident nucleophilic thing, but that reaction follows in one case SN2, in other case SN1, and silver is doing a miracle in the first place, and sodium is not doing that, but it is following a straightforward SN1 type reaction. So, now it is clear what are SN1 and SN2 type reaction. For SN2, methyl greater than primary, greater than secondary, very greater than tertiary, which is unreactive for SN2, and for SN1 just the reverse order, tertiary very greater than secondary, secondary greater than primary, primary greater than methyl. So, this order being followed in SN2 type and SN1 type reaction. I believe this is a very good way to explain the substitution nucleophilic bimolecular or substitution nucleophilic unimolecular reaction. Now, returning back to that carbon nitrogen bonds and its capability, I will take up some more example. I did at the beginning that how can you introduce a how can you produce a carbon nitrogen bond from a simple benzene ring? The answer was by nitration of benzene by mixed acid. It is written here. When ARH, not only benzene or substituted benzene, naphthalene, etc., nitration is being done in a mixed acid, that is Ma, nitric acid and sulfuric acid together. What sulfuric acid does? It takes off the water from nitric acid, generating NO2 plus, and so NO2 enters and hydrogen leaves. So, it is an electrophilic substitution reaction. You end up with ArNO2, and reduction of that ArNO2 will give you the amine, aryl amine. Aniline is a simple case. If Ar is C6H5, it is aniline. So, aniline may be prepared by reduction of nitrobenzene. The overall synthetic sequence begins with nitration of the starting arene and then the reduction. The reduction may be done in number of ways. The dissolving metal reduction of nitrobenzene to aniline. These reactions use metals such as iron, zinc and tin, and typically are carried out at reflux in hydrochloric acid solution, sometimes with added acetic acid, because acetic acid is a very nice thing. It is a not only acidic compound, but also it is a good solvent to dissolve both inorganic and the organic part together. So, a good solvent and acidic in nature. So, sometimes acetic acid helps to dissolve the aromatic compounds, and also it is an acid. So, iron and 30% HCl and heat will convert nitrobenzene to the anilinium chloride, and anilinium chloride to aniline. This is the salt and base being formed by the treatment of OH minus in water. So, I said about the, because aniline is a very nice material in that sense, from here you can make lot of compounds. I gave the list yesterday. By diazotization and followed by Sand-Meyer reaction, lot of functionality could be introduced over there. Another example where the nitration of toluene has taken place, which gives a mixture of ortho and para. Let us take the para is being separated, it should be sterically more preferred. So, para-nitrotoluene when reduced with tin and hydrochloric acid, it will form the corresponding ammonium salt like the previous case. Treatment with OH minus and water will give the para-toluidine. Sometimes catalytic hydrogenation is also good. I will give you a very nice example. Anilines may also be prepared by catalyzed reaction of preformed hydrogen with nitroaromatic. Look at this, para-nitrobenzoate, ethyl benzoate. This side in the 4th position there is an carboxylic ester CO2 ET, ethyl ester, ethyl para-nitrobenzoate. If we reduce with hydrogen in platinum catalyst, in ethanol as the solvent, what will be the product? We will have to think very carefully. There are two groups, one is nitro, another is CO OET. Which one will be reduced selectively? That means whose reduction potential is more. Obviously, nitro will be much easy to be reduced, and if we use sufficient amount or high pressure, then definitely CO2 ET will also be reduced to the CH2H, but under normal condition it is selectively the nitro group will be reduced to amine, keeping the CO2 ET intact. So, this is when two functional groups are there, one selectively could be reduced, especially the nitro group whose reduction potential is very easy to achieve, but hydrogen and platinum could be converted to the amine. So, this is another way to make carbon nitrogen bond through the nitration followed by reduction. That reduction even keeping the other groups which are also reducible intact. Reductive amines are also very important way to make the carbon nitrogen bond. Look at this, we are starting from simple carbonyl compound. Aldehydes and ketones can be converted into amines by catalytic or chemical reduction in the presence of ammonia, because if you reduce an aldehyde or ketone, we will get the corresponding alcohol, or ketone will give secondary alcohol, aldehyde will give primary alcohol. But if we do that reduction in presence of ammonia, then what happens? You see, hydrogen reduction is being done in presence of ammonia, we end up with RCH R prime NH2. What is that? A primary amine, 1 degree amine, NH2 is there. If we do that thing in presence of not ammonia, but R2 NH2, then what we get? We get RCH R prime NH R2 prime. What is that? This is the secondary amine, 2 degree amine. And in the third case, R2 NH R3, that means we are starting with the substituted amine. Then we see no hydrogen directly being attached to nitrogen. So, it is a 3 degree amine or tertiary amine. This conversion can alternatively be viewed as reductive alkylation. You look this way, starting from ketone through the help of amine, we are getting some compound where reduction of the carbon oxygen double bond has taken place. Of course, oxygen has been removed. So, we can call this process as reductive alkylation. So, alkylation is taking place in the nitrogen side and reduction of the bond double bond is also taking place. So, another terminology is reductive alkylation by the help of amine or ammonia and treating with aldehyde or ketone in presence of corresponding reducing agent. What is the mechanism of this reaction? We will try to understand, because whenever a nucleophile is there, an electrophile will be preferred by the nucleophile. A mechanism for reductive amination is addition of the amine to the carbonyl. You see, carbonyl carbon will be positive. Why? Because the carbon oxygen double bond will be pulled towards the oxygen atom more. So, oxygen will be the negatively charged, this carbon will be positively charged. So, H2N R double prime, that is lone non-bonded electron pair on nitrogen, that lone pair will be acting as a nucleophile to attack the carbonyl from the opposite side. See, when we are talking about primary amine, 1 degree amine or ammonia, you will get as a result O minus will pick up the proton from here as OH and remaining thing is NHR, one hydrogen being taken by the O minus, and R and R prime remaining intact. So, this type of compounds are similar to hemiacetal, it is in this case we should call it hemiaminal, because it is not OH, but NHR, one OH NHR. Then loss of water is taking place. How? Because this hydrogen and this OH leaves. So, there is a this type of things is called a beta elimination reaction. This hydrogen leaves, the nitrogen hydrogen bond shifted to make a double bond over here, and OH at the same time leaves. So, two groups leaves at the same time, which are beta to each other, is called beta elimination or E2 elimination, and we end up with an imine. Now, this if this reduction is carried out with hydrogen and nickel or very nice reagent normally not much used, that is sodium cyanoborohydride NaBH3CN, sodium cyanoborohydride, very selective reducing agent. So, what it does, the reduction of this carbon nitrogen double bond will take place, again it is a carbon nitrogen compound, and it will get NHR double prime and H. That means, the hydrogen being added over here, the second hydrogen is being added to this nitrogen. So, two hydrogen atoms being attached in this way. So, this is whether it is primary 1 degree or secondary 2 degree amine, you get this sort of thing. And if it is a 2 degree amine, how the reaction is taking place? The similar mechanism, in this case the nucleophilicity of this nitrogen will be better than this one, because there are two alkyl groups, in this case one alkyl group, but some steric factors also come into play. So, what it will happen? It will attack the carbonyl or add, then you get a hemiaminal exactly in this fashion. Now, the dehydration will take place not through the loss of proton, because there is no proton over here, but nitrogen having the non bonded electron pair. So, it comes over here to make the nitrogen carbon double bond and OH being thrown out. So, it will be water loss and R C R prime will be there, and remaining thing is N R double prime or N R triple prime. And after the reduction, what we get? We end up with the tertiary amine. So, this is the way how the what is the mechanism of the reduction is taking place. There are some examples are being shown. The actual example, say benzaldehyde with the starting material instead of arbitrarily any aldehyde or ketone, treat with ammonia with hydrogen and nickel under pressure and heat it. What will be the product? Now, you can write straight away following this mechanism, NH3, the lone pair nitrogen attacking over here, C double bond O is getting polarized to O minus, and then this proton is getting picked up by that O minus to make OH, then elimination is taking place, followed by reduction of the double bond. So, you get carbon nitrogen double bond is reduced, you get CH2NH2. See, one step with the help of ammonia, hydrogen and little bit pressure and catalyst, you get benzylamine. So, benzaldehyde to benzylamine, if somebody asks how to make it, this is the very nice way to make it. Amination of aldehyde or alkylation of ammonia, whatever way you call it. Say, let us take another example, 2-pentanone treated with ammonia in presence of sodium borohydride or sodium cyanoborohydride. Same thing will happen, you get the NH2 being attached in place of the carbonyl, you get 2-pentanamine. Why? Because 1, 2, 3, 4, 5 longest hydrocarbon chain, it is pentane, the minimum numbering to the substituent. So, it will be 2 amino or 2 amino pentane, or it is called 2-pentanamine. If cyclohexanone is the starting material and dimethylamine is the base or nucleophile, sodium cyanoborohydride is the reagent, you end up with a compound like this, NN-dimethyl cyclohexanamine. So, what we have shown the different types of substrate under condition which follows that amine or ammonia, primary, secondary or tertiary, you can end up with the substrate through from the carbonyl to the carbon nitrogen bond. So, this is a very nice way to make carbon nitrogen bond. One way I said electrophilic substitution in the aromatic system, that is nitration, followed by reduction, Sandmeyer, and put lot of functional group. Even for aliphatic and aromatic, both the cases, this method is in that way is much better. Straight away from putting two reagents, you can get an aldehyde or ketone converted to the corresponding carbon nitrogen, that is CH2NH2 type things. Some more examples are being shown here cyclohexanone. From ammonia and hydrogen you can get this amine, right now we explain. Can you do it in other way? Obviously, answer is we know a very nice reagent, we have studied the Beckmann type rearrangement where an oxime getting involved. So, how to prepare an oxime from a carbonyl compound? Treat with hydroxylamine in presence of acid, you get a double bonded NOH. So, carbon nitrogen double bond is being produced with OH, OH could be removed very easily, do a sodium ethanol. What sodium ethanol will generate? Hydrogen, nascent hydrogen, that will convert this NOH to NH2. The double bond will be reduced and OH and H will leave the system, making the compound cyclohexylamine. So, cyclohexanone to cyclohexanamine could be done in two ways, either ammonia hydrogen nickel or hydroxylamine, making it oxime followed by sodium ethanol. Now, we will take another nice example, 2-phenyl ethanonitrile, CH2C triple bond N, that is triple bonded compound. We want to reduce the triple bond to single bond. What should we do? We will have to do lot of or sufficient amount of reducing agent, that is hydrogen and nickel at 140 degree centigrade. It is found not only that C triple bond N is getting reduced through the double bond to the single bond, that is CH2 CH2 NH2. So, it is now a primary or 1 degree amine, 2-phenyl ethanamine. If it is not an carbonyl compound, not a triple bonded compound or carbon nitrogen triple bonded compound or nitrile, if it is a simple chloride, COCl, acid chloride, benzoyl chloride, how can you convert this to the CH2 NH2? Obviously, you need in that case some amine. Let us take ethylamine is the reagent. So, amine will react with this COCl, this lone pair of electron on nitrogen will attack to this carbon, CO pool will take place, it will be backfired followed by the loss of chlorine. So, chlorine will be eliminated as HCl. So, remaining thing is CO, NH, CH2, CH3. Where the other hydrogen has gone, it has picked up the chloride ion to make HCl. Now, this one when reduced with lithium aluminum hydride in ether, very good reducing agent, mixed hydride in water, what you get? This CO in the similar fashion getting reduced to the CH2 because it is the hydrogen addition. Hydrogen addition is reduction, oxygen removal is also reduction. So, CH2 NH C2H5 is the final product. So, this is the way one starting material or one substrate to another substrate we can play with the functional group interconversions through the knowledge of carbon nitrogen bond formation, carbon nitrogen bond reduction or carbon nitrogen triple bond to single bond or carbon oxygen double bond to carbon nitrogen single bond. So, all these things are being explained with this transparency over here. I showed you all these things. So, now I will end up with one example yesterday, that suppose you want to make, this is the thing I did not say earlier, you want to make an compound which is NR, a 5-membered nitrogen containing heterocyclic compound where carbon nitrogen bond is there. So, you can say yeah, you have seen this type of compound, it is nothing but a pyrrole derivative, only difference is instead of NH I have put NR, that means alkylate pyrrole. If I ask you how can you prepare this type of compound, your answer will be very simple. I told you that break the molecule into simpler component and then you can find out a way to make it. If we write things like this CO, CO, R, let us take R over here. What is this compound? Say R is CH3, CH3CO, CH2, CH2, CO, CH3. So, this compound can undergo ketoenol type tautomerism very easily because it has an alpha carbon atom and any hydrogen being attached to alpha carbon atom can help to get it enolized. This is one. Second point is if I treat with some amine or let me put it in this way RNH2. Now, this amine, the lone pair of electron can attack the carbonyl compound to the carbon atom. Then the electron pair forming the bond between carbon and oxygen will be shifted towards the oxygen atom. And what we see, then in this way we get a very nice thing, that O minus is being formed and N, H, that is and R is there. Now, the nitrogen is tetravalent, so it should be a positively charged. So, this is simple, the attack of the alkyl amine to the carbonyl compound. You can say, why did I take on the left hand carbonyl? Because it is symmetrical. If I take the right hand, it will get the similar compound, no change. So, O minus will pick up this hydrogen, the electron pair between nitrogen and hydrogen will shift on nitrogen. So, it will be nothing but COR is intact in one end, the other side is OH, and this is NH R. Now, there is no charge, that has been satisfied, and one R is already there. Now, what will happen? Very interesting thing. This hydrogen and this OH will leave the system at a time, and it will be eliminated very easily at the same time. At the same time, what it can do, the nitrogen lone pair can also attack the carbonyl compound intramolecularly. This is much energy preferred reaction. So, I am jumping a step over here, and as a result I can show you that you end up with, okay, let me write down, no problem, R N H. If I keep it intact, then there is a new bond being formed between this nitrogen and the carbon. So, what is the thing? 1, 2, 3, 4, 5. Now, if I write that thing, that anti-elimination has taken place. So, the structure of this compound will be converted to, this nitrogen is there, R is being attached, there is a double bond in this side and this side is R, and I can put an OH. And exactly in a similar fashion, another two hydrogens are there, the anti one will prefer to be eliminated to end up with a nitrogen R double bond R, and there was an R over here. So, you are able to make pyrrole starting from very simple acyclic compound, a diketone in that way. I will end up today's thing with one more nice case or nice example. If the problem is like this, a heterocyclic nitrogen containing compound, and if somebody asks you how can you convert a 5 member to a 6 membered compound. These are very known compound. This is a pyrrole and this is pyridine. As I explained the other day, pyrrole is acidic in nature, pyridine is basic in nature. Those are all carbon nitrogen containing compound, and I can say that it is doable. What is the difference between this and that? There is one carbon more in that case, and how to add one carbon and then play with that substituent. You know one reaction, I will tell you that if you recapitulate that reaction, it will be very clear that if you convert the pyrrole to N minus, that means the proton of the pyrrole being picked up by the base. Let me put a base like sodium ethoxide. We know sodium ethoxide gets polarized to OH minus and Na plus. So, OH minus will pick up this proton, make the nitrogen minus with the lone pair of electron, and the counter ion will be the sodium ion. So, pyrrole salt is being produced with the help of sodium ethoxide, and I need one carbon. So, how to get one carbon, and that answer is very simple, that is the sodium ethoxide itself can help. So, in presence of a very interesting compound called chloroform, anesthetic, but interesting thing is carbon chlorine bond, 3 carbon chlorine bonds are there and 1 carbon hydrogen. So, if you treat with sodium ethoxide the same reagent, what will happen? This has done with the pyrrole, this acid base sort of thing, but it can done a very nice reaction over here, that this negative charge can pick up this proton and then the bond between carbon and hydrogen can shift over carbon. Now, the carbon will be pentavalent, it will have to lose one carbon chlorine bond, and that will happen. And then ultimately what is remaining? We get Cl, Cl and a non bonded electron pair on this carbon. What we call this type of species? Look at, very nice. I think definitely we are calling this type of species as carbene, a bivalent carbon. But if I ask what type of nature this carbene possesses, is it electrophilic or nucleophilic? Then you get confused that there is a non bonded electron pair. So, it might act as a carbene. Yes, carbene can act as a nucleophile under different condition, but in this particular case, if we count the number of electrons around this carbon, 2 pairs of bonded, that is 2 plus 2 4 with 2 chlorine atoms, and the non bonded electron pair whose spin normally is being opposite, this is called the singlet carbene. So, total number of electrons around the carbon including the non bonded electron pair is 6. So, its octet is not fulfilled. So, obviously, it will be electrophile or electrophilic. So, carbene is a very interesting species in that sense. It has a non bonded electron pair, but it is mostly under the normal condition is electrophilic in nature, and you have studied one reaction for sure. You know, if I take phenol and treat with chloroform and alkali, CHCl3, the alkali may be sodium hydroxide or sodium methoxide. What will be the product? You know this reaction from memory or from other thing, you can say that we will end up with orthohydroxybenzaldehyde and a mixture of parahydroxybenzaldehyde. That means, this aldehyde group is coming in the ortho and para position, because the phenolic OH group is ortho para orienting, and where from this aldehyde is coming? Through the formation of this carbene, which is an electrophile, because electrophilic substitution reaction is facile in case of benzene ring. In phenol, it is getting activating the ortho and para position. So, same sort of thing will happen over here, but in case of pyrrole, what will happen? The lone pair of electron now will add to the carbon having the 2 chlorine group attached. So, this sort of addition species will be formed, and then this lone pair shifts over here and this bond breaks and one of the carbon chlorine bonds leaves the system. As a result, what you get? You end up with a 3 chloropyridine, very nice way. So, I have given one synthetic method for pyridine through pyrrole, or I have also suggested that one 5-member nitrogen containing heterocyclic compound could be converted to the 6-member nitrogen containing heterocyclic compound by this way. So, in brief, carbon nitrogen bond formation, carbon nitrogen single, double, triple, all those bonds, playing with that bond like nitrile, taking the carbon as the nucleophile, nitrogen as the nucleophile to get very interesting molecules, amides. Then, as I told at the beginning, that carbon nitrogen bonds are very much present in living system, and almost everyday life we need. Our life is made up of this carbon nitrogen bonds in many ways. So, I believe this 5 lecture series will help you to understand or to get the gist that without this carbon nitrogen bond people cannot exist, because all this amino acid, the peptide, proteins, alkaloids, many medicinally important compounds are antibiotics are coming from this carbon nitrogen bond, the beta lactam. Thank you very much.